All right, looks like it's a good time to start. Hello, everyone. Welcome to CS292F Convex Optimization. And this is the fourth lecture of the class. Welcome. So let's, I see that we have like 25 people joining the call, 26. Let's maybe wait for another 2 minutes. Yeah, so during these 2 minutes, so let's talk a little bit about the logistics. Next week, next Monday, the homework 1 will be due. If you haven't started yet, it's a good time to maybe start doing it, so that you can decide whether you have to spend the weekend to work on the homework. So the late homework submission policies of this course is that I think you have a fixed number of days in total for all the 4 homeworks. So if you use them up, then you use them up. So you can have a number of days without additional penalty, which you can allocate to your own schedule accordingly, to make room for all the other things like conference deadlines that you may have, and travel plans that you may have, and coordinating with other courses and so on. So that provides a flexibility, but it's a good idea to start doing homeworks early, because the lectures will in fact depends on some of the things that you get intuition about from a homework. So you'll see some of those in today's lecture. Okay, looks like we have 34 participants, so I think it's a good time to get it started. So today we're going to be talking about gradient descent. So this is the first lecture on the actual convex optimization algorithms. So we will get into the details of this algorithm. We'll talk about how do we measure its computational complexity, and how do we, under what family of convex optimization problems can this algorithm be used to obtain the optimal solution with computational guarantees and so on. All right. So so last time we took a look at the canonical problem forms and gave a tour with many examples from linear programs, quadratic programs, second-order Cohn programs to semi-definite programs. We talked about the optimization hierarchies, and how each LP can be represented as QP, how a linear program can be generalized to semi-definite programs, and how conic programs are the most general form of all programs, by taking the Cohn constraints to be, say, the second-order Cohn, to be the first quadrant, the non-negativity Cohn, and also the semi-definite Cohn to recover the LP, SDP, and the SOCP, and how the quadratic programs are part of SOCP. And in the end of the last lecture, we talked about we talk about the example of max cut, which tries to solve an NP complete problem approximately using convex relaxation. So that's a good example with a pretty short but not so straightforward proof of the approximation ratio. So I hope that is one of the motivations for those more theory-minded people that learning convex optimization and learning semi-definite programs, convex relaxation, and all the techniques that we learn in this class will be very helpful to you to your research career. Okay, so today we're gonna be talking about gradient descent. So we'll start by explaining the algorithms, the gradient descent algorithm, and the different components of it, like learning rate, the gradients, and what is a reasonable learning rates to choose. And then we'll give intuitions about what if we choose different learning rates and what would the behavior of the algorithm. We'll also be talking about the data dependent way of choosing the learning rate adaptively using line search techniques. In particular, we'll focus on backtracking line search. And after that, so maybe in the second half of the today's lecture, after we take the 5 minutes bio break, we'll move on to talk about the convergence analysis of gradient methods. Specifically, we'll be talking about the convergence for smooth convex problems. So we define what smoothness means. We'll talk about smooth and, in addition, strongly convex problems, and proving that they satisfy different computational guarantees, and they have different speed of convergence. And meanwhile, we'll be talking about the different style of convergence. So what do we mean by sublinear convergence? What do we mean by linear convergence? What do we mean by acceleration? And whether these guarantees are optimal. Finally, we'll be talking about generalizations of these convergence results to potentially non-convex optimization problems, to problems that converges linearly without requiring, say, strong convexity. So we will be talking about weaker version of strong convexities that will allow us to prove linear, by linear convergence, this means it converges exponentially to the optimal solution. It converges really quickly, and takes only a logarithmic number of iterations in order to converge, right? So we'll be talking about polyak Lojasian, the PL condition. So I never get, I can never get hold of like how to really correctly pronounce this. So perhaps like some of you guys can teach me how to pronounce the Lojasiewicz condition and its related parts. So if we still have time left, then we'll be given like a specific example in the context of machine learning. So we'll be talking about gradient boosting and cast it as some kind of a gradient descent algorithm. All right, so that's a plan for today. So let's get it started. So for the interest of today, we'll be considering the form of convex optimization problems with unconstrained, smooth objective function, right? So let's not worry about having constraints. Let's think about the simpler problem with only an objective function to maximize, to minimize, and f is convex, differentiable, we'll talk about what smoothness means. In fact, in order to obtain the computational guarantee, we need the we need this function to actually satisfy the so-called strong smoothness, which is a little bit stronger than smooth, which we'll define very shortly. But for now, let's take a look at the algorithm, the key algorithm that will be the topic of the entire lecture. Okay, so gradient descent is an iterative algorithm that starts from some initial point. So this can be your favorite initialization. For instance, it can be x0 equal to 0. So you can start at the origin, and then it repeatedly update the parameter x by moving towards the negative gradient direction with a step size of, say, tk. Okay, and after you run gradient descent for a number of iterations, then you stop. And the hope is that at the time you stop, now it is at the kth iteration, and then you can show that this xk is a nearly optimal solution comparing to the best possible solution globally in R to the n. Okay, so we'll be denoting the optimal objective function value as f star, and we'll be denoting the solution that attains this optimal criteria value by x star. So again, whenever we have star, even if you are out of the context, then it's a good idea to assume that, at least within this class, to assume that we are referring to the optimal solution and optimal objective, the optimal objective function value. Okay. So a little bit of more intuition. So when we choose this learning rate or this step size, this tk, to be infinitesimally small, then the gradient descent becomes like a continuous process where you are moving towards the direction of the gradient flow in a continuous space, right? So these lines draw, like if you start from the different initializations that are circled, then tracing the direction of the gradient everywhere. At the end of the day, like for any convex function, you'll end up converging to the same solution. Okay, so so just think about that. You're skiing and you're on the top of a mountain, and then you are following the steepest way down the slope, and as you keep skiing, and at the end of the day, you will converge to the base station, and no matter where you start and which lift that you took to get to the mountaintop. Okay, so so when you have a discretized steps, on the other hand, so you won't be moving towards a continuous flow, but instead you will move towards a discretized version of this flow, which looks like something like that. You're moving towards this, and then a little bit there, a little bit there, and a little bit there, and ultimately you'll end up getting to the final solution. What if the objective functions is non-convex? So in this case, the gradient descent algorithm still makes sense. It still makes a lot of sense actually, because it tries to find the locally optimal solution. But then for non-convex objective functions, then the initialization actually matters. So depending on where you initialize, you may end up converging to different locations of the space, and some initializations are better than other initialization. In this case, for those trajectories on the left, you converge to the solution on the left. And for whenever you are on the right-hand side of this ridge, then you will converge to the right solution that's on the right-hand side. Okay, so in other words, for non-convex function, it is in some sense unrealistic to hope that without worrying about which initialization that you are at, and you will always converge to the global optimal solution. But instead, maybe we can talk about how quickly it converges to a local optimal solution. As a matter of fact, we won't even be able to prove that today, but we will be talking about how gradient descent for non-convex optimization problem is able to converge to a stationary point that satisfies the property that the gradient is approximately 0. Okay, so think about like certain non-convex optimization problem having a really flat region, that whenever you hit those regions, then you're not going to move any further. But those regions might be a saddle point rather than a local minima. Okay, so that's what we're gonna be talking about when we get to the non-convex optimization problem. Okay, so one way to interpret the algorithm of gradient descent is to think about it as doing like a local quadratic approximation of the function, and then try to solve the local quadratic approximation optimally by finding the arg mean. Okay, so here's here's how it works. So think about this as a Taylor expansion of function f of y at location x. So think about this as a Taylor expansion. For those who are not familiar with Taylor expansion beyond the one-dimensional case, so this is simply like a vector-based generalization of the Taylor expansion. So in a place where you have derivative, now you have vector, and when you have vector, then you take the inner product of this vector with the with a difference of y minus x. So now both of these are vectors, but taking the inner product will make it a scalar again, right? So now we are basically taking the first order Taylor expansion with an additional residual term that's used as a quadratic function to keep things within the local neighborhood. Now let's think about yeah. But by the way, like suppose this parameter t is chosen to be sufficiently small. The last term is always non-negative, then we will end up getting an upper bound of the original function f of y. So you can think about this as first constructing a quadratic upper bound, and then try to minimize this. Then try to minimize this upper bound by solving this. Since the quadratic function have a unconstrained quadratic function has a closed form solution that you can get by setting the gradient to 0, then maybe this is something that can be easily solvable. So let's work it out. Let's work out a minimum of this quadratic approximation to convince you that this actually reproduces the gradient descent algorithm. So let's take the gradient, okay, of the right hand side with respect to what? With respect to y, right? So when we take the gradient on the right hand side, we get so the gradient of this f approximation, okay, is equal to gradient of f of x, right? So this is the gradient of this term, and then the gradient of the second term will end up being, just by the chain rule, you get 1 to t multiply with 2 multiply with y minus x, right? So this will be the gradient of the quadratic approximation. So now let's set this gradient to 0. By setting this gradient to 0, we can work out the optimal solution for y, and let's see what y is. So first of all, these two got canceled out. So you get y minus x is equal to minus t times gradient of f of x. And that gives us the gradient descent update rule, y is equal to x minus t gradient of x. So that's one way to interpret what gradient descent is doing, right? So specifically, if we want to visualize this using this figure, let this solid line be f of y, okay, and this will be the local quadratic approximation at location x, right? So so notice that we choose t appropriately such that this quadratic approximation is always the upper bound of the original function that we're trying to minimize. Therefore, if you move from this blue dot to this red dot, the corresponding solution will always decrease the objective function value by a little bit, by a bit that's in some sense, as we'll see later, proportional to the square of the gradient at this location. Okay. So what is a reasonable step size to choose? So first of all, it is often okay that we simply take the step sizes to be constant for all iterations. But if we do this and then we choose t to be too large, then gradient descent may or may not converge. So think about this two-dimensional example. So now what is plotted with this ellipses? They are the objective function value contours of the objective function. So think about this as so think about this as these lines of a quadratic function. Okay, so if you look at this from top down, then it gives you this kind of figure with the contour lines drawn. And then suppose we start from here, then we take the gradient direction is perpendicular to this contour, right? So this is a gradient direction, but now we are moving this large, right? So once we move here, then with a step size t, then we evaluate the gradient again, then the gradient is towards this direction, but taking the same step size, now that the gradient, taking the same step size that's somewhat large may get us somewhere that's here, okay? So once we're here, then taking the gradient direction here with the same step size may move us like very far away from where we are. So in this case, it keeps it keeps diverging, and then we'll get larger and larger objective functions, and it will never really converge to the optimal solution. Okay, so suppose we take the learning rate or the step size is t to be something that's very small, very close to zero, then we are closely approximating the direction of this gradient flow instead of jumping like a leaping frog. So that'll work. That'll certainly work. But if t is chosen to be too small, then it will take many iterations before we converge to the optimal solution. So take an example of minimizing the same function using gradient descent and starting from the same initialization. If we take t to be something that's very small and run that for 100 steps, we can see that it is making progress towards the optimal solution, but it gets like extremely small. So it may take another 1,000 steps before it makes substantial progress towards getting to the optimal solution. So when if we choose this learning rate parameter t to be just right, then chances are like we are able to converge to the optimal solution with a very small number of iterations. So in this case, when we choose t appropriately, then it takes only 40 steps that we get nearly a point that's nearly indistinguishable visually from the optimal solution. Okay, so the question is like, how do we, for each problem separately, how do we choose this learning rate appropriately so that we can guarantee that we converge to the optimal solution just fastest possible with fixed learning rate. So that's something that the convergence analysis of this algorithm will teach us how to set the learning rate. Okay. So and before we get to the analysis for fixed learning rate, I'd like to like continue on the algorithmic front by talking about a particular way to choose this to choose this learning rate adaptively without needing to know anything about this function itself. Okay, so this approach is called backtracking line search. Okay, so so this procedure have two hyperparameters that we need to set. Beta and alpha. So typically we set beta to be 0 somewhere between 0 and 1. So we can set beta to be half. Without losing too much generality, we can basically set beta to be half. And alpha, we can also just set alpha to be half, in fact. So essentially, if you just want an algorithm to work without hand-tuning how well it works, then setting beta to be half and alpha to be half is going to be provably effective for your problem. Okay, additional fine-tuning of this hyperparameter will make it a constant factor faster, but that's really not required for the interest of just optimizing something. Okay, so let me first talk about how backtracking line search works. So we will start with some initial learning rate, t equals to say t init. So for instance, we can set this t init to be 1, right? And then in every iteration, the algorithm is gonna try moving along the negative gradient direction with step size of t, and then check whether it actually gives us sufficient descent. Okay, so what do you mean by sufficient descent? So by choosing t, the parameter t, we wanted to make sure that that this condition is satisfied. We wanted to make sure that, notice that this is while this condition is true. That means that while not this fx minus t gradient of fx, so this is updated location x plus, while this thing being smaller than fx minus alpha t gradient fx squared is not true, then let's decrease the learning rate by multiplying that with a factor between 0 and 1. That's decreasing let's decrease the learning rate exponentially with a parameter beta. Okay, and once we get to a point where this condition is true, where this condition is true, then we commit to that learning rate and then perform the gradient descent update accordingly. Okay. So this is saying that we start from some crude upper bound of learning rate that can potentially work. If it doesn't really work, then I decrease the learning rate by half. And if it still doesn't work, I decrease it another time by half. I keep doing that until I get to the point where this learning rate becomes appropriate for this local neighborhood that we are actually getting a descent. Okay, so that's the idea of backtracking line search. Graphically, we can interpret backtracking line search like using this one-dimensional figure. So think about this as a restriction of the linear approximation of a restriction of the linear restriction of this function f towards one direction. Okay, so on the horizontal axis we have this learning rate t. On the vertical axis, we have either this function at updated location, or all these dashed lines. It denotes a linearized version of these denote the linearized version of the function f at location x. Okay, the key difference is that the gradient when we choose alpha to be say half, then the gradient got scaled by a factor of half, so it doesn't go down as quickly, right? So notice that by the definition of convexity, we know that this line always is a lower bound of is always a lower bound of this convex. Of this convex function, simply by the definition of convexity. In other words, we know that as we keep decreasing t, right? As we keep decreasing t, say from this location, this is our t init, right? As we keep decreasing t, we'll always end up reaching a region where the condition is true, where the sufficient descent condition is true. Okay, so for us, so this illustration is more general because it considers cases when we're iteratively updating the parameters towards the direction that's given to us by delta x. But for the interest of gradient descent, like we can simply take this delta x to be the negative gradient direction. Minus gradient of fx. Okay, so in which case we can. So when we take is there a way that I make this thing smaller? Okay, so when we take the delta x to be minus negative gradient direction, so we can see that this becomes f of x. Right, minus alpha t gradient f of x squared, right? And this becomes the f of x minus t gradient of fx. Okay, so notice that like I said, this region is the interest region that we want to find a particular learning rate that works. So that geometrically refers to this region. That is saying that this is larger than f. This is larger than f of x minus t minus alpha t gradient of f of x. Minus. Yeah, so that Yeah, so that gives us the that gives us a sufficient descent with the choice of learning rate chosen adaptively by backtracking. Okay. So now like suppose we use backtracking with alpha and beta both chosen to be 0.5. Then for the same example and initializing at the same location, it takes a total of like 12 iterations in order to get to somewhere that's roughly the same optimal solution, right? So there are like 12 outer loops, and in total it's like 40 steps in total. Like 40 steps it measures the total number of steps you take and then evaluate objective functions. So each outer step may take several rounds of trial and error by shrinking the step sizes until you find one that satisfies the sufficient descent condition. So in total, it takes the same number of iterations, so a much smaller number of iterations, and the same number of like steps contemplating before you actually take an update of your parameter. Okay, so there's another way of doing line search. So that's called exact line search. So sometimes it is useful to do this, but more often than not, the backtracking line search is just good enough. Because if you want to do exact line search, then you would like to find the smaller, the learning rate choice that minimizes this objective function. So this is relatively easy to solve because you can use, say, because you can use things like bisection. So why is that? So the reason why you can do exact line search and solve this optimization problem efficiently is because this is a univariate optimization problem. This is a univariate function of S alone. And also, since we've seen that for any convex function f, when we restrict to a particular direction, then that one-dimensional function remains convex. So that means that this function as a function of a parameter s is actually a convex function. Therefore, if we know the largest s that gets us out of bound, then we can already start from there and then do bisection. And with log 1 over epsilon number of iterations of function evaluations, we can end up getting to an approximate exact line search solution. Yeah, so but doing this, unless you have a closed form solution for this, which often you don't for general convex optimization problem, this is something that's often not worthwhile. But we'll see that for either line search approaches, we'll end up getting the same theoretical guarantee as the results of the using a fixed step size according to some property of the function itself. Okay, so the advantage of doing line searches doesn't really increase the speed of convergence like by orders of magnitude, but it does make a difference in practice. So the recommendation for practical usage of the gradient descent algorithm is to do backtracking line search, because exact line search, it takes too much time in every iteration with unclear benefits. Okay, so so there's a question from Roman about can you elaborate on what bisection is? Okay, so I'll do it here. So this is the S parameter. So notice that we're optimizing over S, and this line is a convex function that's restricting this convex function f towards the direction of minus s gradient of f of x. So this is the one direction towards the gradient direction. So the line search, the exact line search tries to find this point. Okay, it tries to minimize the f of x minus s gradient of f of x. So this is convex, first of all, and by bisection. So here's what I mean. So you can first try to search where this location is by starting, say, from 1. Okay, so you double it to make it 2, and compare this with the evaluation of 1 to see whether this is smaller, okay, or bigger. If it is smaller, then you keep doubling it to make it 4. So now you are here, right? Now you are here. When you compare these two, it is still small. So let's doubling it again. Let's double it to 8. Now we get somewhere that is a that is a bound that we know that the optimal solution at this point is contained between these two between these two boundaries. Okay. Now we can do binary search, right? So first of all, by checking that this one is bigger than that, we know that the convex function started increasing, right? So now now that it started increasing, then we can start doing bisection by looking at these 2 points. Okay, we will first find this point and then check whether whether the midpoint of this is increasing or not increasing, and by checking that, we'll discover that the optimal solution is on the right-hand side. Then now let's recursively call this bisection by finding this point, and then it will tell us that this region is what contains the optimal solution. So with say k iterations of doing this, we're able to narrow it down to half k accuracy, right? So that gives us an appropriate learning rate that's approximately the argmin. I hope that helps with your question. Right? Okay, so so here's the convergence bound, or the computational guarantee for the gradient descent algorithm. Okay, so let's first make some additional assumption about this function f. So previously we've talked about f being convex and f being differentiable. In order to formally show that we have a like polynomial time like convergence computational guarantee, then we need to make an additional assumption that this function is strongly smooth. So by strongly smooth, I mean the gradient of this function is actually Lipschitz continuous, right? Specifically, the gradient of this function satisfies this inequality. So that's the definition of Lipschitz, of any function being Lipschitz, right? So this is also known as L smooth or L strongly smooth. Okay, by saying something is smooth, it basically says that the gradient is smaller than positive. Gradient is bounded without specifying what this L is. So yeah, sorry. It's basically saying that the Hessian is. Yeah, it's easier to explain with this function being second order derivative. By saying something is smooth, it basically says that the second order derivative of this function satisfies that the spectral norm of this spectral norm or like operator norm is finite. So this is smooth. By strongly smooth, in addition, this requires that this is smaller than some constant L, right? So we're making it explicit that this is smaller than the L, rather than just anything that's bounded. Okay, so suppose we have this additional condition, then by setting any fixed step sizes that satisfy that it is smaller than 1 over L, then we can show that after k iterations of gradient descent, the suboptimality, so this is the difference between the objective function criteria of the kth iterate and the optimal and that of the optimal solution, is smaller than something that goes to 0 at a rate of 1 over k. Okay, so the same result also holds for backtracking line search, but with the parameter t replaced by something else. Okay, so so we say that gradient descent has a convergence rate of 1/k. So alternatively, we can talk about the iteration complexity. So iteration complexity measures if we pre-specify the epsilon suboptimality gaps that we wanted to achieve, and how many iterations does it take to get to that to get to that point. So notice that if epsilon is on the order of 1/k, then this is equivalent to say that the k that achieves this epsilon parameter is on the order of 1/epsilon. Right, so we'll use these two ways of talking about convergence rate interchangeably. So sometimes it's more convenient to talk about the something that goes to 0. Sometimes it makes sense to talk about iteration complexity. So this is called iteration complexity. Okay. When there's an additional condition that holds about the function f, so we can hope that the algorithm will converge even faster. So specifically, we talk about the convex functions, and if the convex function actually holds strongly with parameter m, so in which case we say that this function f is m strongly convex. Then notice the duality. Notice that the analogy between strong smoothness and strong convexity, right? So we say something is m strongly convex, and sometimes we say that a function is L strongly smooth. So in this case, if we in addition assume that the function is m strongly convex, and again assuming the L strongly smooth condition before, then we can show a much faster convergence to the optimal solution. Specifically, let's parse this theorem a little bit. So if we set the fixed step size t to be something that's smaller than 2/m plus L, so notice that this is a little bit bigger than say t equals to 1/L as we've chosen previously, and in fact choosing this is always smaller than 2m plus L. Okay, so choosing this learning rate works for this case. So whenever we choose this t to be within this range, then we can show the geometric convergence that goes to 0. So this is a constant, and this c to the power of k, where c is something in between 0 and 1. Okay, so what we'll see today is that we can prove that this c is, we can take c to be equal to 1 minus m over L. Right, so in this case, we can say that with k iterations, and it goes to 0 exponentially rather than on the going to 0 at a rate that's say 1/k, that's polynomially. Okay, so let's calculate the corresponding iteration complexity. So suppose we have the suboptimality to be on the order of c to the k. If we just invert everything over, and notice that this c is between 0 and 1, we can write the number of iterations k to be log I guess log if we take log on both sides, then we get k log c multiply log epsilon and then k is equal to log say since c is between 0 and 1, so this is equal to minus log c inverse. Now minus log c inverse is something that's positive, then we can move it to the other side and get k equal to like C inverse, and this is something that's on the order of log 1 over epsilon. Okay, and the constant C got hidden inside this big O notation. Okay, so how close this C is to 1 actually matters, right? So in particular, in this case, using the identity that 1 minus say 1 minus 1 over say k to the power of k as k goes to infinity. So this is equal to anyone can tell me what this is? 1 over e with a natural natural log natural exponential. So this is basically saying that suppose we have a C that looks like that. It takes L over M, roughly order of L over M iterations to shrink the gap, the suboptimality gap epsilon by roughly 1 over e. 1 over e. Okay. Okay, so so this kind of a geometric convergence is called linear convergence. And the reason why it is called linear convergence, so it must sound like very counterintuitive. So previously we have something that goes to 0 at 1 over k, where k seems to be something that's linear. Here now you actually have exponential convergence, but we're not calling it exponential convergence, but we're calling it linear convergence. So the reason is the following. So if we plot the convergence on the vertical axis, let's plot the suboptimality gap. On the horizontal axis, let's plot the number of iterations. So the geometric convergence is called linear convergence because it looks like a linear line on the semi-log plot when the vertical axis is on the log scale and the horizontal axis is on the linear scale. So similarly, like suppose we have 1 over k convergence, then on this semi-log plot, then the convergence will be much slower, and you will see a convergence curve that's way above this linear line. So in that case, we're saying that any polynomial convergence is called sublinear convergence, and any exponential convergence is called linear convergence. So I guess let's spend a little bit more time to understand the conditions before I start writing down proofs about the guarantee. So first of all, so by saying that something is Lipschitz continuous, by saying the function satisfies the Lipschitz continuous, it's equivalent to say, especially when the function f is it's twice differentiable, it is equivalent to say that the largest eigenvalue at any location x of this Hessian matrix of function f is smaller than L. So equivalently, this is saying that in the semi-definite ordering, you can dominate this Hessian by an identity matrix that looks like L times I, right? So it makes more sense if you start to think about the quadratic optimization problem, in which case the Hessian is independent to the input x. So in this case, when we think about linear regression with this quadratic optimization problem, the Hessian is always x transpose x. This means that the largest eigenvalue of this Hessian is a square of the largest singular value of x, which we can simply take L to be this parameter. On the other hand, the strong convexity of a function f actually measures, in some sense, the smallest singular value. So so generally, like if we say a function is strongly convex, then this function needs to be lower bounded by say mx squared. So even this function needs to be I guess even this function needs to be convex. On the other hand, when we take the second derivative of the whole thing, then we end up getting the Hessian of function f is minus, I guess, m identity needs to be positive semi-definite, which gives us this condition. Right. So again, in the special case of a quadratic function, when we are solving a linear regression, then the second derivative of this vector function of this vector input function is the same at x transpose x, regardless of what the input is. So in this case, we can take m to be the smallest eigenvalue of the Hessian, or the smallest singular value square of this design matrix X. So notice that when X has more variables than you have data points, so P is larger than N, so this is a high dimensional case in linear regression, then F can never really be strongly convex, unless you add additional regularization terms such as those in ridge regression. So even if when the smallest singular value of X is larger than 0, we could potentially have a large condition number, which says that L over M can be relatively large. So this might be the context where people heard of the term condition number. So its natural generalization in convex optimization problem is simply L over M. So the gap between so the ratio between the strong smoothness parameter and the strong convexity parameter is what we call condition number, and that will be the that will be the term that we'll be referring to in the remainder of today's lecture, and also whenever this Lipschitz constant and gradient Lipschitz constant and the strong convexity parameter come up in the remainder of this course. Oops. Okay. So in practice, in practice, we need to know like when to stop gradient descent. Like when can we be sure that we're at a solution that's nearly optimal? So of course we can evaluate the objective function, but that only gives us f of x. So we still do not know what f star is. So luckily, for strongly convex problems, we can actually certify that the solution is nearly optimal by looking at the size of the gradient. Okay, so one particular stopping rule is to say that whenever the gradient at the current iterate is sufficiently small, then we can stop, because we know that we are already nearly optimal, right? So so the way to see this is to just apply the property of strong convexity. So again, by just applying the property of strong convexity, by definition of the first order condition of strong convexity, we get that I guess f of x for any x is larger minus a gradient of f x minus I see. So yeah, forget it. This is this is the wrong side that we are applying this first order optimality condition. So there's a property in a homework that you will derive that gives you this direction by saying that you can upper bound the saying that you can upper bound the objective function value using the size of the gradient if you rescale that with a strong convexity parameter m. Yeah, let's forget a proof of this for now, and later in a proof of the convergence, and when we introduce a different other weakened condition of strong convexity, everything will become much clearer. Okay, so the pros and cons of this algorithm gradient descent is that it's really simple. So all you have to have access to is to evaluate the gradient. So as long as you can evaluate the gradient, then you can run each iteration by just moving towards the gradient direction, and the complexity is simply proportional to the dimensionality of your argument x, right? So so when the problem is strongly convex, it's well conditioned, it's actually very fast. So it converges exponentially to the optimal solution. So taking only a logarithmic number of iterations isn't going to increase the computational complexity more than a logarithmic factor than a linear time algorithm that you actually need to even represent the solution in the first place. On the other hand, the first order optimization often suffers from issues where f is not strongly convex, or like if the condition number is poor, then basically you'll end up having to work with the sublinear convergence that goes to 0 at 1 over k. So that can be much slower, and in some problems it becomes unacceptable because you never really get to like really high accuracy and high numerical precision solutions to that optimization problem. Another issue is that we actually need the function f to be differentiable. For non-differentiable functions, for non-differentiable functions, we don't really know like how to solve it yet. Okay, so so there's a question. There are two questions. So let me address them now before we go to this 5 minutes break. So the first question from Yu-Xiang is that does strong convexity imply L continuity? Okay, so so strong convexity doesn't imply L smoothness, strong smoothness, and Boyd and Vandenberg chapter 9.1 use M instead of L. So L and M, they're not the same thing. But we'll see in the later part of the course that they are actually closely related to each other by duality. So a quick forward to that result. So any function f that is strongly smooth, L strongly smooth, implies that its conjugate, its convex conjugate, is actually 1 over L strongly convex. Similarly, if any function is M strongly convex, then the dual of that, the conjugate of that is 1 over L smooth. Okay, so they are related in a slightly different way. That's very elegant. So you will see a little bit of that from the homework, where you can see the symmetry between these two conditions, and that will help you to build the intuition towards understanding duality and understanding how the conjugate actually works and how to convert one to another. But there could be functions that are strongly convex, but not but not strongly smooth. So I'll give an example here. So function that's M strongly convex but not smooth. Okay, so take one function that is M strongly convex. Let's take another function that's M strongly convex. So we know that when we take this is F1, this is F2, if we take the maximum of X1 and F2, so this is a pointwise maximum, we know that pointwise maximum of a function is pointwise maximum of a function is actually is actually a convex, right? So in this case, it is also strongly convex. You can prove that by definition. But notice that there is a point here that is not differentiable, right? For any point, any function that's not differentiable somewhere, then it can never really be smooth because the gradient changes very rapidly here. Okay. So the second question from Kaichi is not what I'm not sure what you mean. Okay. So Kaichi is trying to respond to Yi's question. So I hope that that's helpful. All right, so let's take the 5 minutes break, and then we'll come back and then talk about the analysis of the convergence for gradient descent. Okay. Yeah, we'll resume at 2:05.
Hi, Professor. Can you hear me?
Yes.
About the question I asked.
So you are E, right?
Yes. I understand that this example and the strong convexity doesn't imply L continuity, but on the book, the BV book, when it says there's an upper bound on the Hessian of fx, and they use the capital M. That's the Hessian of fx is like
yeah. So in that notation, that M is our L. So I think they might be using capital M and then the lowercase m to denote the two things. So we are using capital L like to be consistent with the idea of gradient Lipschitz. So it is L. And M, the small case m denotes the the smallest eigenvalue of the Hessian everywhere. So that would be the strong convexity parameter.
Yes, and then what I'm confused is that in that it says the equalities or when they talk about strong convexity, that imply the sublevel of the set is bounded, and then the set is bounded, and then they have an upper bound for the, and then they derive that the Hessian is less or equal to capital M times I. And they don't use anything, they don't say anything, there's any condition, but they just derive the strong convexity.
The strong convexity of what?
They just go from the strong convexity to the L continuity with like two sentences. They don't say anything like you should satisfy this condition so that the Hessian is less or equal to Mi.
Yeah, so when you talk about a semi-definite upper bound of Hessian, then it says nothing about strong convexity. It basically says about the strong smoothness. And in order to talk about the strong convexity, you need a semi-definite lower bound of the Hessian.
Yeah, but the book basically saying that based on there's a lower bound, there's upper bound. That's what they said.
So maybe it's using duality, but I'll take note of your question and respond to that separately because I don't have that book with me right now.
Okay, thank you so much.
Okay, yeah. Okay, so it's 2:05. Let's resume the lecture. So we'll yeah, I think we'll talk about okay. So let's talk about proof. So let's talk about actually proving this theorem right here. Okay, let's try to prove this theorem here. So let's move to so the first components of the first components of the convergence of gradient descent is to show that it is actually a descent method. Okay, so convergence of gradient descent. And again, let's set up the problem. We're trying to minimize f of x by assuming that f is differentiable. So there's a gradient, and the algorithm is simply keep updating x k plus 1 equals to x k. Okay, so with a learning rate t, and you are moving towards the gradient direction. So for simplicity, we'll talk about the current iterate to be x, and the next iterate to be x plus. So this becomes f and x plus. Now, the first thing, like I said, the first thing that we wanted to prove is that the gradient descent actually monotonically decreases the objective function value. So let's use the condition that we are assuming. So by the L gradient Lipschitz condition, or the L smoothness condition, we can apply the first order condition, or the something like a Taylor expansion, right? So by showing that x plus minus x transpose gradient of f of at x right? So notice that the reason why we can write this as a valid upper bound is because L gradient Lipschitz condition. So in some sense, over here, this term is x plus x. This term is x plus minus x transpose L over 2 identity, half L, and then x plus minus x, right? So since this is something that dominates the Hessian at the location at anywhere. So for any psi, then this becomes a valid upper bound. So notice that you can get this by applying Taylor's theorem to say that on the line segment between x to x plus, then there is something where you can take that Hessian and this inequality holds by equal, right? So that's by Taylor's theorem, and then you can apply this semi-definite ordering to get this condition. Specifically, this is something that I asked you guys to prove in homework 1. Okay. So with this, now let's try to substitute the algorithm into here. So by substituting the algorithm, we know that x plus is equal to x minus a gradient direction. So we end up getting minus t gradient f at x transpose gradient of f at x plus half L, right? So this is t gradient of f at x. Wait, why am I having this? Okay. Let's simplify the expression a little bit, since gradient transpose gradient simply give us a magnitude, square magnitude of the gradient. So we have f of x minus t gradient of fx square plus half t square L, t gradient of x square. Well, okay, let's combine the last two terms. We get f of x minus 2t minus t square L. So now it is clear, like why we want to, in the assumption of that theorem, why we want t to be smaller than 1 over L. Because if we do that, then we can replace one of this t in this t square, one of the t in this t square to be 1 over L. That cancels out with this L. So if we continue with the derivation, then we can get f of x is minus t minus half t gradient of fx. So this gives us a descent lemma, right? So let's write it down. Lemma so if we choose t to be larger, if we choose t to be smaller than 1 over L, and f obeys L smoothness, then for any x, fx plus is smaller than f of x minus half t gradient of fx. So this lemma is saying that the gradient descent, if we choose the learning rate to be sufficiently small, then it monotonically decreases the objective function value, like in every iteration. So with that, and by running t for many rounds, we can already see that the gradient descent will end up converging to somewhere if the final objective function is lower bounded. But then we want to actually construct a finite iteration guarantee, and that's why that's what we're going to do next. Okay. So with the descent lemma, let's now apply convexity. So notice that the descent lemma has nothing to do with convexity. So we're only making an assumption about f that is smooth, that is L smooth. Now let's apply convexity. Okay. So so by the convexity and by the first order optimality of condition of convexity, we know that fx star is larger than f of x plus gradient of f of x transpose and x star minus x, right? So notice that we can this holds for this is basically saying that at any location x, if we linearize the convex function over there, then we'll end up getting a lower bound of the original function. We're basically substituting the y parameter, which we can choose arbitrarily, to be the optimal solution x star. Okay, so now let's apply the descent lemma. Okay, so so again by descent lemma, so we know that fx plus is smaller than f of x minus half t the gradient of fx squared, right? So let's apply this descent lemma to construct a lower bound of f of x by moving the minus t something to the other side, right? So then we can replace this f of x with f of x plus, but then we can add this half t gradient of f at x. Okay. Now I'm copying the remainder of this equation here. So notice what we get. We get a quadratic term, we get a cross term, but there's something missing, right? So there's something missing before we can combine them into something where we can complete the square. So let's just add it and then subtract it. So let's add half t 1/2t x. Let's add the other like square term on the right hand side and then subtract it away. Okay, so this follows from the descent lemma. The first thing follows from convexity. Okay, so now we can combine these three. So that gives us f of x plus, let's extract 1/2t, and then we get something that's cleaner looking, right? T square. Okay, and then minus 2t. Okay, let's now complete the square. So we get f plus 2t 1. Once we complete the square, we get x star minus x plus t gradient of f of x square minus. Okay, but what is this? Right, so this is the same as minus x plus, right? By the algorithm of gradient descent with step size t, right? So so that allows us to write f of x plus plus x plus square minus star minus x. Okay, so that gives us the first chain of arguments. So notice that there's this very nice telescoping structure. So we add something that's x star, then we subtract the points that you are starting from, right? So now let's telescope. By applying the same thing that we get to different x. So let's apply this to x 0 to x1 all the way to xk. Okay, let's do that. And then we get f star, x star on the left hand side. And then this is greater than f of x1 plus half 1/2t x star minus x1 square x0 square, right? Let's do that for the second iteration. So you will have x2 plus half t x2. And we can do that for everything until the kth iteration. So that will give us xk plus x star minus xk square minus xk minus 1. Okay, let's now add everything up. Okay, so as we add everything up, then we have the telescoping structure that keeps canceling out with each other. Well, this one does not actually cancel out. This one, right? So after this, we end up getting k times f star on the left hand side, and then this is larger than the sum of I from 1 to k f of xi on the right hand side, plus this additional terms. So all the leftovers, that's 1/2t. We have the positive one, that's x star minus xk square. We have the negative part, that is x star minus x0. So this is your initialization, right? So let's divide both sides by k, and then maybe move this term to the left-hand side. So we get 1 over k, I from 1 to k, f of xi smaller than f star. Let's move this thing to the other side, and then dropping the negative term, because we can bound the negative term by 0. So we get plus 2t1, since we're dividing k on both sides, so we have a k here. Then we have x star minus x0 square. Okay, so the only thing that remains is to how do we connect the left-hand side with xk, right? Xk is the last iterate. So notice that by the descent lemma, we know that fk as I gets larger decreases monotonically. So f of x1 is actually larger than f of x2, larger than f of xk. Therefore, we can lower bound the average by the minimum, right? So the minimum is going to be f of k. Collecting all the results together, we get the desired result, minus f star. So this is suboptimality. It goes to 0 at a rate 1 over tk, x star minus x0 square. Okay, that completes the proof. And the theorem that we can write is that choose t to be smaller than 1 over L, and f is L smooth. Then okay. Yeah, so that recovers exactly the results given in this theorem. Okay, so any questions about the convergence proof before I move forward? All right, so we'll see like more of such analysis today, and then later in the remainder of this course. But all the arguments that we applied in the convergence proof of the standard gradient descent is gonna come back. So make sure you understand every single step of it, and trust me. So once you understand them, the whole thing becomes more intuitive than at the moment. It seems pretty magical that we somehow construct a telescoping structure. But it is a telescoping structure. It is almost always a telescoping structure that allows us to prove some kind of nonlinear, sublinear convergence bound in the form of 1 over k, or 1 over square root of k, and so on. So there are like several techniques, this being one of them, to construct this telescoping structure.
Yeah. Could you briefly just go over the whole proof again, just like just talking about what properties you use, just like pointing them out?
Okay. Okay. So
because
was it not clear?
No. Well, because I was trying to write it down and follow through. But there were some parts that, like you said, because of certain proofs, or because of certain properties, like yeah.
Yeah. So the descent is the descent lemma clear? Like which parts specifically that you're referring to?
Well,
So the descent lemma uses basically the first inequality is uses the definition of L Lipschitz gradient, gradient Lipschitz property,
right? And
then the and then we're basically not using the convexity at all. Then we apply the algorithm. Then we apply the learning rate smaller than 1 over L.
Okay.
Right. So in then in a second step, when we apply convexity, so the first step basically applies the first order condition of convexity, and the second step applies the descent lemma.
Okay.
So after that, it's basically trying to complete the square and then construct this x plus from everything else.
Okay.
And form the telescoping structure. So once
Okay.
we have that telescoping structure, then everything becomes straightforward. You just add everything up and then divide everything by k.
Okay.
Right. So so the lectures will be recorded, and
Yeah.
and I can share also the handwritten notes. And it's actually better written in LaTeX from the scribe notes that's already there
Okay.
for the gradient descent lecture.
Gotcha.
Yeah, so feel free to revisit them and then refer to the recorded lecture again.
Okay, sounds good.
Okay.
Thank you.
So you get like more proficient with these arguments as I keep doing the same thing again and again. Okay. All right. So let's. So one question is whether this is the best possible, whether gradient descent can be improved. Right? So for the family of functions with Lipschitz gradients, so it turns out that gradient descent is not actually the optimal algorithm. So consider the first order, the family of first order methods being those that works with gradient and keeps doing things that are similar to gradient descent by moving towards a direction that's maybe the gradient or maybe like any functions in the span of the gradient of everything, all the points that we visited before. So this is a so-called Krylov space method. And this is also a formal definition of what we mean by a first order methods. So the first order methods basically uses only the first order information that we have collected so far, right? So with this definition of a family of methods, we can talk about information theoretically. What is the best use of this information to construct solutions that optimizes this objective function f? Okay, so Yuri Nesterov very famously constructed pathological examples of functions in the infinite dimensional space that provides this such a lower bound, saying that for any methods that's within this family of first order methods that uses only gradient information, you have to satisfy this condition that you cannot get faster than 1/k squared. Okay, so notice that the gradient descent has 1/k, but the lower bound now have 1/k squared. So it turns out that so you can actually construct algorithms that achieves 1/k squared that converges much faster than the standard gradient descent for the family of methods that are gradient Lipschitz. Okay, so this is called the accelerated gradient methods, also called Nesterov acceleration. So we won't be able to talk about this today, but hopefully we'll revisit the acceleration later in the later part of this course. Okay, so how about non-convex functions? So at the very beginning, we talked about the convex functions. If we minimize it, no matter where we start, it all ends up at the same location, right? But for non-convex functions, since we can't really get that, and so we cannot really talk about convergence to the global optimal solution or competing against the f star, that's optimal objective function value. Instead, one way to talk about the extent to which the gradient descent have converged to in non-convex optimization problem is to talk about first order condition of optimality. So a necessary condition of that is the stationarity, saying that the gradient is 0. So notice that this is differentiable function, differentiable functions and unconstrained. So the gradient equals to 0 characterizes all stationary points. So this includes local minimum, local maximum, and all those stationary points. Okay, so we can actually talk about the convergence of the gradient descent for non-convex problems by establishing the rates of the gradient converging to 0. Okay, so So notice that we have a sublinear convergence with 1/1 square root of k rate on the absolute value scale of the gradient of the gradient operator, and it can be shown that this rate cannot be improved because you can construct lower bounds, information theoretic lower bounds, saying that there are like a family of non-convex optimization problems. If you are successful on some of them using the gradient information, then you are necessarily you will necessarily fail on one other optimization problem that has the same information that you observe up to this extent. So in some sense, when you use gradient descent to minimize an objective function when it is non-convex, and all you know is that it is smooth, has satisfied Lipschitz gradient, then the gradient descent is already the best algorithm that's out there computationally. Okay, at least up to a constant factor. So the proof of this theorem is actually revealing. So let's like go to the scrap notes and then talk about the proof of the convergence of in the non-convex case. Okay, so convergence of gradient descent on non-convex but L smooth function f. Okay, so so actually the only thing that we need is for proving this is the descent lemma. So again, notice that in the descent lemma we don't actually require the function to be convex. So again, by the descent lemma, so let me rewrite it here. So this is saying that if you take the gradient descent step, the f plus is smaller than f of x minus half t gradient of f at x. Okay, so this is a descent lemma. So let's actually apply this directly to the iterate. So let's apply this for k from 1 to k. Okay, so first of all, fx fx2 smaller than fx1 minus half t gradient of fx1, right? Then fx3 is smaller than f of x2 minus half t gradient of fx2. And okay, so f of x k is smaller than f of xk minus 1 minus let's write one more, k plus 1 smaller than f of xk minus. Okay, so let's sum them up, and then when we sum them up, a lot of things got canceled out, right? So when we sum them up, so these two got canceled out, and these two got canceled out, and these two got these two got canceled out, and this two got canceled out. So so at the end of the day, let's collect everything together. We end up getting the fxk plus 1 smaller than f of x1 minus half t, and then sum of I from 1 to k, so you get the gradient of f at xi. square, right? So now let's divide, let's move this system about the sum of the gradient to the left-hand side and then divide both sides by k, right? So you get, so you get 2t over k, sum of I from 1 to k, gradient of fxi square. This is smaller than fx1 minus f of xk plus 1, right, over k. Okay, let's further divide both sides by t to make it closer to what we want, and then move this 2 to the other side again. So we get this expression. Now notice that f star is always smaller than fxk plus 1, right? For all k. So we can further bound this by tk fx1 minus f star. Okay, so again, we can use the same idea that to bound the minimum, to bound the lower bound the expectation with a minimum. So this is minimum over all I in 1, 2, 2k, and the square of the gradient norm. So now the left-hand side is smaller than the right-hand side. So the only thing that remains, if we look at the theorem statement, the only thing that yeah, this is already it, right? So by taking the by taking square root on both sides, we get minimum of I in k. Smaller than square root of tk and 2 fx1 minus f star. Right. Of course, you can further bound this by using the Lipschitz property of the objective function, but that's not really required. So we can use a gradient Lipschitz property to bound f1 minus f star with the arguments, but that's stick to the statement that we wanted to prove. Okay. So just to take a step back and look at the proof. So all we are actually using is a descent lemma, and then we're telescoping directly by canceling out the functions in the iterate, and then by constructing the gradients themselves, the sum of gradients. Since everything canceled out in the telescoping part of the inequalities, we can divide the gradient by 1 over k. Square of gradient by sum of the square gradient by 1 over k, and that gives us something that goes to 0 on the right hand side. But what does this say? This is essentially saying that over the course of k iterations of running gradient descent on these non-convex functions, in at least one of the locations, you end up running into a point that's epsilon stationary. Right, so you can always check that. You can calculate the you can calculate the norm of the gradient, and then keep the point so far that has the smallest gradient norm. And at the end of the day, you can always output that. Okay, so I hope that's clear. Okay, so that's everything that I talked about in a point format. Yeah, everything should be clearer from the handwritten notes. Okay, so now that we've covered the proof of the gradient descent for gradient Lipschitz functions, and also for gradient Lipschitz and convex functions, and we end up getting the 1 over k rate. So the only thing that I didn't prove you that I stated earlier is is a linear convergence for strongly convex problems. So so actually, I'm gonna be proving something that's stronger than the statement before. So I'm gonna be proving the linear convergence under weaker conditions on called the Polyak-Lojasiewicz condition. Okay, so before that, I'll talk about this condition. I'll talk about other weakened version of strong convexity that's out there. So whenever you run into that in academic papers, and you won't be scared of these conditions. So more or less they are like a part of the proof, and how much of whether you can get away with the same conclusion by assuming something that's weaker. And there are some interesting materials here. So I'll go over the definition of these conditions in details. In particular, I'll be focusing on restricted strong convexity and the PL condition. But there are other things like growth rate condition and the and so-called error bounds condition. They are more or less equivalent for convex and smooth functions. Okay, so first of all, like restricted strong convexity is weakened version of strong convexity. So from homework 1, you should have seen this equivalent definition of M strong convexity for differentiable functions. Okay, so for any differentiable function, it is M strongly convex if and only if this condition is true for all X and Y pairs. Okay, so this form of inequality is something called a secant inequality. Okay, so restricted strong convexity tries to weaken directly this version of the definition. So you can say that you can instead of saying that this inequality holds for all X and Y in the entire domain of this function f, you only need like two conditions, and you wanted to say that these definition and this condition holds only for a subset of pairs of X, Ys. So in fact, you can the restricted strong convexity is saying that f is convex first of all. So there are two legs, and in the second leg it says f obeys these conditions that's similar to this equivalent definition of strong convexity, but by substituting this y into the projection of this particular x into the solution set x star. So we've already shown that So we've already shown that this thing is convex, right? We've shown that for any convex optimization problem, this x star is a convex convex set. Therefore, we can talk about the projection of that, and notice that the optimal solution is given to you by the normal cone, right? So this is something that I hope you will continue to get further insight. But for now, let's look at the analogy between these two equations. The first one is for all xy, but the second one is for all x, but with y taken to be a specific thing. That's a projection of this x to the optimal solution set. Okay, when the optimal solution is unique, then you can replace this x projection to be simply x star. Okay, so let's like build a little bit more intuition about restricted strong convexity. So in what sense that RSC is weaker than M strong convexity? So in fact, if we look at the second RSI condition, the restricted secant inequality condition alone, it doesn't actually imply convexity. That's why we need to further assume that this is convex. So here are like the family of examples where you have a non-convex function, but it satisfies RSI. Right? So notice that for any point that's on the right-hand side, the projection of it to the optimal set is always the origin. Right? On the other hand, like the function is getting larger fast enough to the point that for all x, the RSI is actually true. Okay, so Also, restrictive strong convexity, functions that are restrictively strong convex doesn't necessarily needs to be strongly convex. So here's a simple like one-dimensional example. So if you just split the quadratic function into two halves and then add a flat region in between from minus beta to beta, and all points within this region are optimal, so this is a function that's clearly not strictly convex, let alone strongly convex. On the other hand, you should expect this function to be as easy as a quadratic function to be minimized. So these are the kind of functions that are captured by RSC, but not by strong convexity. More interesting examples that actually motivated the definition of restricted strong convexity are like problems like high-dimensional linear regressions, like lasso. So it has been shown that in high-dimensional linear regression, when scenes are generated and satisfy some relatively weak regularity condition, then you can prove that those functions are restrictedly strongly convex, satisfy RSC. And that's a key technical tool that people are using to prove the linear convergence of lasso estimators using gradient methods, using gradient descent, until you reach the point where you enter the region of statistical like indifference. So basically, your algorithm will converge exponentially to an epsilon, where beyond that, it doesn't really make sense to optimize further, right? So that's you're getting the best of both worlds. So since optimizing an empirically observed function will leads to overfitting, so this is saying that, well, for those solutions that are not overfitting, then you can get the optimal solution, nearly optimal solution that's near enough, and beyond which you are going to overfit, and you can get to that region exponentially fast. Okay, so so this allows us to talk about high-dimensional Hessian that has a lot of zeros in their eigenvalues, but still, if the solution happens to be within the span of those eigenvectors that correspond to non-zero eigenvalues, then the function actually satisfies the restricted strong convexity. It was also shown that the RSC is in some sense always needed for if you want to show that the gradient descent algorithm converges linearly. So this is in some sense an if and only if condition. So this theorem is upper bound part of it that says that if so for any functions that's L smooth and M RSC, then you can establish this kind of a convergence from your initialization to the optimal solution by this iterative shrinkage. In every iteration, you are getting 1 minus M over L closer to at least one of the optimal solutions. Okay, so this doesn't actually directly give us a suboptimality bound, but you can make use of the Lipschitz condition to actually show that this at the end of the day will imply an optimal solution measured in terms of the suboptimality. So we won't be talking about that. So I'll leave this answer to this question as a quiz question. So anyone who finds a solution to this, please post it on Piazza. Okay. So there are other conditions that can be used to guarantee linear convergence. So these are the PL condition, the quadratic growth condition, the error bounds condition. So all of these talk about specific things that we can say about this function that we're minimizing. In particular, in the PL condition, this is saying that the objective function, the suboptimality can be upper bounded by the gradient. So this is something that I teased you I teased you a little bit earlier. So how do we, when we talk about how do we certify the suboptimality by measuring the norm of the gradient? So we know that convex and strongly convex functions satisfy this condition, but maybe this condition is all we need. Maybe there are other functions that are not strongly convex that actually satisfy this condition. And with this, then maybe that's sufficient for us to establish linear convergence. Quadratic growth condition, on the other hand, sits on the flip side. This is saying that the suboptimality can be lower bounded by the difference between your x and the one particular optimal solution that's a projected that's a projection of x to the optimal to the space of to x star, to the space of optimal solutions. Okay, so error bound condition, on the other hand, tries to bound the same thing. It tries to upper bound the distance between the set of optimal solution using the gradient. Right? If either of these three conditions are true, then we can establish that if in addition the function is convex, yeah, actually, if either of these conditions are true, then we can establish linear convergence of the optimization problem. This even includes those functions that are not convex. But if in addition f is actually convex, then all these conditions are essentially the same. So with one you can derive all the others. So maybe you lose a little bit in the parameters. But when you think about these problems, it's this family of the set of the set of functions that satisfy these conditions with certain m that are bounded away from 0. Then if in addition you assume f is convex, then all these are equivalent to each other. Okay. So for the remainder of this lecture, I'm gonna talk about how the PL condition can be used to prove linear convergence. And then I'm gonna show you how strong convexity implies. So M strongly convex functions are also satisfy MPL condition. And that will give us one particular proof of the linear convergence of the strong convexity, strongly convex functions that we've seen earlier at the beginning of the lecture. Okay, so that's the plan. So let's get to it. Okay, so it's already like 2:53. So please just hang around for a little bit further. This will be pretty quick. Okay, so first of all, I will show that f obeys MPL condition, and this implies linear convergence. In particular, I'll show that fxk is smaller than fl plus half L 1 minus m over L to the power of k x minus x star square. Okay, so proof. First of all, by descent lemma, this is something that we've been using for several times, and we can get that f of xk smaller than f of xk minus 1 minus t gradient of fxk minus 1 square, right? And now I recall that the PL condition tries to use the gradient to bound the suboptimality. So we can just apply MPL condition, and that gives us fk minus 1 minus mt Okay, so recall that the PL condition, so I'm gonna write it here, is saying that half of the gradient at any x is larger than m times the suboptimality. Okay, so this simply involves applying this condition to derive this inequality. Okay, so once we have that, once we have that, let's move this to the other side. Let's subtract the f star from both sides of the equation. So we'll have xk minus f star smaller than f xk minus 1 minus f star minus mt f xk minus 1 minus f star, right? So let's group these two terms together. So we'll have 1 minus mt f k minus 1 minus f star, right? So that gives us a recursive equation of this shrinkage that shows that the suboptimality actually goes to 0 exponentially. So this gives us f x k minus f star is smaller than 1 minus m t to the power of k f x star fx1, so this is our initialization, minus f star, right? So so we can take t to be 1 over L, so this gives us a shrinkage ratio of m over L, and then we can apply the Lipschitz gradient condition. We can apply the Lipschitz gradient condition to further bound this. Right, so simply use a first order optimality condition, and that allows us to bound this term further with half L x1 minus x star square, right? So this is by this is by Lipschitz gradient. Yeah, so this concludes the proof of the exponential convergence that we've stated at the beginning. Okay, so the last thing that I wanted to do is to connect everything back to strong convexity. So implies a PL addition. Okay, so here's how it works. By strong convexity, f star is larger than f of x plus gradient of f of x, x star minus x plus half m, x star minus x. So this is simply by first order condition of a definition of strong convexity. So so now let's do the trick of constructing that completing the square trick that we've used before in our proof of gradient descent by when applying convexity. So now we're applying strong convexity, right? So we can apply strong convexity and then add and subtract x, add and subtract the missing term in the form of the gradient, the norm of the square of the norm of the gradient, and that gives us so far I'm just copying everything over by extracting the common factor, and then we can add the gradient of f of x square. We can subtract the gradient of fx square. Okay, so by after doing that, we get 2m over 1, and then we can complete the square by constructing this m x star minus x minus plus the gradient of f of x minus half m. Okay, so now now notice that this is always positive, right? So we can essentially lower bound this by simply replacing this by 0. Okay, so now this one goes away. Then by just rearranging terms, we end up getting the PL condition with parameter m that's in the form of m fx minus f star. Okay, so that completes the proof for strong convexity is weaker than PL condition. Okay, so I guess we'll skip this example and maybe we'll revisit it in the next lecture. And for all the materials that I talked about, you can find them in these references and further readings. And they are also very nicely compiled in the script notes from the last time I was offering this class. Thanks all for coming, and the lecture video will be posted sometime later today.